Hello and everybody, welcome to our geometry class. Today we will be talking about section 7.4, which is on SAA or AAS, and also the HL theorem. These are the last two types of ways to show two triangles can be congruent to each other. So as of right now, we have SAS, we have ASA, and we also have SSS. So now we're going to go ahead and fill in all of the rest, so then that way we have everything in our tool bag. All right, so here, as we mentioned, the first thing we're going to talk about is going to be the SAA congruency. And then afterwards, we're going to talk about the last one, which is the hypotenuse leg theorem. And that's basically kind of like the special case of the SSA. So we'll talk about how that works out in just a little bit. Okay, so let's go to our first part right here, which is proving that SAA actually works as well. So you can see in the picture, this is the SAA situation that we're given. In the picture, we can see that F is going to be congruent to C. We also have given as B is going to be congruent to E. And then lastly, AB, the length, is going to be congruent to DE, the length. So those are two triangles on the right-hand side. And what I'd like to do is prove that those two triangles are congruent. So then that way we can use this as an actual theorem. So what I'm going to do is I'm going to go ahead and focus on the length of BC, which is located right here, and also focus on the length of how it's related to EF over here. Now, according to trichotomy, there are only three things that can happen. Those two lengths can either be equal to each other, which is case 1, or BC could be greater than EF, which is case 2, and lastly, BC is going to be less than EF, which is case 3. Needless to say, what's going to happen is we're going to probably eliminate case 2 and case 3 in the process. So then that way we can kind of force it to be only case 1. So that is going to be our tactics in this case. Okay, so here let's go ahead and look at case 1. What if BC is equal to EF? Well, let's go ahead and make the mark in the triangle below so you can see what's going to happen then. So if BC right here is equal to EF, then that means that the two triangles are congruent to each other by ASA. So that is going to tell me that, oh, those two triangles are good to go then. And that gives me what I want. So by ASA, the two triangles ABC would then be congruent to triangle DEF, and then we're pretty much done. So that's the ideal condition. Now, let's go ahead and look at case 2. What if BC is smaller than EF? What if BC is smaller than EF? Then what I'm going to do is, if you notice in triangle ABC, I've extended BC the line, so then that way we can go out as far as we can so that it becomes equal to EF. So basically what I'm doing is I'm going to go ahead and introduce a point on BC the line such that BC prime is going to be congruent to EF then. So let me kind of write that right here. So extend, let's see, BC to point C prime such that BC prime is going to be congruent to EF. So this is going to be my point plotting postulate or theorem. Okay, so if I've extended it that far, then that means that the two triangles now, ABC prime, okay, and also EF, these two are going to be congruent to each other. Looking at the picture, then these two triangles are congruent to each other by SAS. So that's fine. And then by corresponding parts, now this is the part that you have to watch out for. This angle F would then be congruent to this angle C prime by corresponding parts. Now, at the same time, that angle F is congruent to this angle over here, which is going to be ACB. And needless to say, that is an impossible situation because if you look at those two angles in the first triangle, they can't be congruent to each other because one is an exterior angle, the other one is going to be a remote interior angle. And we learned that in the last section. It has to be the case where the exterior angle is always greater than the remote interior angle. All right, so this is going to be our contradiction right there. Last case, well, case number 3, if my computer can show up, right there, is what if BC is going to be less than EF? Well, I think what we can do is do a similar case of what we just did. So this time around, what I'm going to do is I'm going to take BC and I'm going to introduce another point C prime so that it is actually shorter, but still nonetheless is going to be congruent to EF, which is on the right-hand side. So this length right here, BC prime, is going to be congruent to EF over here. So just like before, these two triangle ABC prime is going to be congruent to triangle DEF by SAS. So you can see it right there, S, and then A, and then S once again. Now, same as before, then that means that C prime, let's see, where I have the angle, AC prime B, this angle right here should be congruent to this angle right here by corresponding parts. And just like in case 2, that's an impossible situation because once again, we have a remote interior angle which is equal to its exterior angle, and that is going to contradict our exterior angle theorem. All right, so there it is. We've eliminated case 3, we eliminated case 2, so that means case 1 is the only case that's possible. So by trichotomy, then that means that the two triangles are congruent to each other, no other exceptions. All right, so there it is. Now, let's go ahead and look at the next one, the last one, which is called the hypotenuse leg theorem. The hypotenuse leg theorem is kind of like a special case of the SSA situation or ASS situation, where you have two sides and then an angle that is not in between the two sides are congruent to each other. The only time this works is if you actually have a right angle. So that's the special condition here. The angle part, has to be a right angle. And in terms of what else is given, well, the other two things that are given would then be a hypotenuse and also a leg. And hence, that's why it's called the hypotenuse leg theorem. So here's the picture underneath. Let's go ahead and see how this works. In the picture, we're given that AC is congruent to DF. So AC, that is here, those are the hypotenuse. Then we have CB is congruent to FE, so that's this right here and this right here. Oh, actually, I wrote that wrong. Let me go ahead and change that a little bit if it's okay. In this picture, at least the orientation is wrong right now. We are given that AB is congruent to DE. So my fault. It's still the leg, but it's just like put it somewhere else, unfortunately. And then the last part is that, like we said, the angles that are congruent to each other are 90 degrees. So angle B is a right angle and angle E is a right angle. Now, if you want, you can say that they're congruent to each other, but I prefer you say that they're right angles because this is the only way that this theorem will actually work out. So that means that this is going to be congruent to this. And what I want to do is I want to prove the two triangles are going to be congruent to each other. ABC is congruent to DEF. All right, so here's how the proof works then. In this case, we're going to go ahead and introduce something also so you can see how these two triangles are going to be congruent. I want to introduce a point Z on FE, the line, such that E is going to be in between those 2 points, F and Z. And also CB, the length, is equal to EZ. So once again, we're going to use the point plot theorem to help us out in this case. So on the second triangle right here, here's what I'm doing. I am going to extend FE right here, right? I'm going to go ahead and extend the line. And I'm going to extend it to a length so that it is congruent to CB, which is located right here. Okay, so I'm going to take these two lengths and I'm going to make them congruent to each other. By introducing that point, we're going to go ahead and call Z. Okay, and if we want, we can go ahead and create DE, which I definitely think we should. All right, so let's see here. Look at the first triangle, ABC. Okay, look at the other triangle, DEF, the one that I just kind of created. According to what we have, I do believe that DEF and DEZ are supposed to be linear pairs. And if there's a right angle there, then that means that the other part, DEZ, is also going to be a right angle. Well, looking at the two triangles, once again, we have ABC, this triangle, and we have this triangle over here, which is DEF we just created. I do believe that they are congruent to each other by SAS because if you notice, they do share the side right here, and then we share the angle right here, okay, and then we share the side right here. So by SAS, we can say that triangle ABC is then congruent to triangle DEZ. Now, just looking ahead, most likely what I'm trying to do is I'm trying to show that triangle DEZ is then congruent to triangle DEF next to it. Because if I can do that, then that means that since one triangle is congruent to another and the second triangle is congruent to a third, by transitivity, the first and the last triangles are going to be congruent to each other then. All right, so now that we have those two triangles that are kind of like drawed out, marked up and everything, are congruent to each other, let's go ahead and look at some corresponding parts. I know that by corresponding part, because because AC is a marked right here, then that means that DZ should also have the same mark because of corresponding part. And look what happened. This mark DZ is the same thing as DF from the very beginning because that was given, that AC is congruent to DF. Well, what I have in FDFZ is that we have two triangles. Let's not look at DFE and DEZ as two triangles, but rather one big isosceles triangle. And if that's the case, then that means that their opposite angles are going to be congruent to each other. So going to the opposite angle right here, I know that this angle is then going to be congruent to this angle right here. So let me go ahead and make that mark. And again, by corresponding parts, angle DZE, right, is the same as this angle ACB. So if this angle is congruent to this angle and this angle is congruent to this angle, then that means that angle F in the original triangle is going to be congruent to angle C in the original triangle. And lo and behold, just let me use a different color so because it's getting a little bit too messy. Here in the original triangle, we have C, we have F, those are congruent to each other. We have B, we have D, E, F, which are congruent to each other. And finally, we have AB, and then we have DE, which are congruent to each other. So now we can say that by AAS, because that's what we proved previously, the two triangles that we want to show, ABC, would then be congruent to each other to the other triangle DEF then. Okay? All right. So that one's out of the way. Now we actually have our full artillery. So the conclusion is that we have the following ways to prove two triangles are congruent. We have SAS, which we've been using forever. We have ASA, we have SSS, and now I've introduced the last two, which will be AAS, or you can say SAA. And then the last special case is called HL for hypotenuse leg theorem, right? You don't have to write the theorem part. You could just say HL. And that's going to be the special K of SSA or ASS. Okay, so let me show you as a proof, how does the HL actually work? Because for AAS or SAA, I'm pretty sure you get the idea because it falls in the same category as all the other all the other three that's on that row. Okay, so here's your sample problem. In this picture, what is true is that we're given DH is going to be perpendicular to DJ. So that is where the right angle is right here. Then also JK is going to be perpendicular to DJ. So that's a right angle right there. Finally, I have JH is congruent to DK. So you can see those are given as blue line segments. And what I would like to do is I'd like to prove that H is going to be congruent to K, the angles. So that's located right here and right here. Now, because I see some right angles, the first thing that comes to mind is HL in this case, because well, we just basically did a proof where you use hypotenuse legs. So what I'm going to do is I'm going to go ahead and isolate the two triangles that I think are congruent, and then let's see if we can prove that they are congruent according to the given. So here we have triangle DJH, and then you can see that I have the right angle, as we said right here. And then we also have triangle DJK on the bottom, and then we have the right angle down here. And we're also given that DK is going to be congruent to JH. So we have the right angle, we have the hypotenuse, now we're missing a leg. And if you look carefully, those two triangles, they share DJ as a side. So I definitely can use the reflexive property there. But there it is. There's our hypotenuse leg. So now we can go ahead and use the proof. So here's what it's going to look like then. So first, I'm going to go ahead and order them just as we would for any other theorem that we've been doing using congruent triangles. I'm going to go ahead and start with the hypotenuse. So first, I'm going to go ahead and say that JH is congruent to DK because of the given. Then that's going to be my hypotenuse part. Next, I'm going to say DJ is equal to DJ because of the reflexive property, and that's the leg part. Now, can I say S and then some sort of angle afterwards? The answer is yes, but I want to use specifically HL, or I want the author to know that I'm specifically using the hypotenuse leg. So that's why I'm writing H and L instead of like side and side. Okay, the last part, we have DH is perpendicular to DJ. JK is perpendicular to DJ, that's given. And from there, we can then form our right angles, and that's the definition of perpendicular. Remember, in HL, we don't have to show that those last two angles are congruent to each other. We can just show that they're right angle, and that's sufficient enough. Now we have everything. We have the hypotenuse, we have the leg, we have the right angle, and then therefore, we can say that the two triangles are congruent to each other. Do you actually have to go in that order of a HL and a right angle? No, the answer is no. You can go right angle, leg, and hypotenuse, whichever one you want. Any one of those three you can show in any order. It's not as specific. Sorry, this one is actually very specific because you're showing hypotenuse and leg and right angle. But whereas like side angle side, I need to make sure they're consecutive. So that's why I need to show it in a certain order, unlike this case. Well, nonetheless, we are done because the last thing is corresponding parts. So angle H is then congruent to angle K. And then we are finally done. All right, so hopefully you are able to understand